let's say if it's a three-flavored theory, yes, then you have your 8 Goldstone bosons, plus if this U1 axial was a true global symmetry, yes, then there would be a corresponding Goldstone boson to that U1 direction as well. So that is the particle that we call the eta prime. Yeah? So that's why we like it so much, because again, it's a particle that would be a Goldstone boson, but it's not. And the way it's not a Goldstone boson is very strongly related to the actual dynamics that is giving rise to confinement in QCD. Okay. So the eta prime, because it would be a Goldstone boson, would also shift under this anomalous U1 axial transformation. Yes. So the effect of the anomalous U1 axial transformation is A, to shift the eta prime, yes, B, to shift the theta parameter. Okay. So that means that one combination of the two, yes, one combination in particular, for example, this combination theta minus f eta prime is the quantity that is invariant under the axial symmetry. So you can use that combination. So the expectation is that that combination is the one that is going to be showing up in your eta prime potential. Okay. So you can kind of have a Spurian analysis if you promote the theta to a Spurion, yes, and then this combination is the one that is invariant under the axial rotations, yes, because we have the theta shifting by f times the angle of chiral rotation, and the eta prime is shifting it by the same thing without the f factor. Okay, very good. So now we know that the U1 is anomalous, so anomalies are often manifesting themselves in the presence of instanton configurations. So the most plausible expectation that I guess have many people have been thinking about initially was that, okay, so that means that instanton effects are actually going to raise the mass of the eta prime, and that's why it's not a massless particle, not a very light Goldstone boson. Okay, so we could then try to see if this was sort of the right dynamics that is explaining the presence of a mass for the eta prime, what kind of chiral Lagrangian term would we add? Yeah, so we can just try to do the usual story that we have for QCD. Yeah? So the U is again the same Goldstone matrix that I outlined in the previous on the previous page, which has the usual pions and the eta prime in it. Then here we have the usual term that is an explicit breaking term. It is due to the presence of the quark masses. Yeah? So that's that you can again guess using Spurian analysis. And then you can ask the question, so what is the term that is going to be generating for you the eta prime mass? Yes. So again, it's supposed to be invariant under all the usual global, the non-anomalous global symmetries. Yes? Yes?
Sorry, so eta prime is the QCD axial.
In some sense you can, well, eta prime is not the QCD axion as you think it for dark matter, yes? Eta prime is a particle whose mass is of the order of, lambda QCD. It's almost a GeV. I forgot exactly what the mass, 900 MeV or something like that. Eta prime is an existing particle.
Okay? It's the meson with anti-upward, and down, anti-down.
Right. So yeah,
it's like eta.
There's eta, yes, and then there's eta prime.
Okay.
Right. I don't remember exactly what the composition is of, in terms of quarks, but yeah. So it has the usual. You can write it in terms of the quark content, etc.
Yeah, it's the SU3 singlet.
Yeah, it's probably just all of them the same.
Singlet,
yes. It's just
Goldstone
U bar,
boson.
D
It's not
bar
really
plus
a
SS
Goldstone
bar.
boson.
Right. But the important thing, so this is an existing particle. So this is not a hypothetical particle. Yes, we're talking here about this is ordinary QCD here. Yes. So So this is, here we didn't make up any fairy tales yet, about having another global. This is QCD.
So, I mean, you haven't said anything about large n, right? I mean, the eta prime is only light.
So we'll get to that. So that's going to be one of the stories that is going to come as the large n. Yes.
What does AMSB stand for?
Anomaly mediated supersymmetry breaking. I will explain that also.
Right.
Yes. But it's not important yet. It's when I try to sort of, have a cousin to QCD where I introduce supersymmetry and then get a similar kind of theory. That's an explanation. For now, just QCD. Okay, very good. So good. Thank you for these questions because it means that I need to explain things a little more. I'm trying to ask the question if there was so we know that the eta prime is massive in QCD. It's pretty heavy actually, like I said, close to a GeV. So it's almost like just another generic meson in the theory, not like the pion or the kaon, which are much lighter than the usual QCD scale, as like the proton, etc. So then you can try to ask the question: which term would you write in order to capture the eta prime mass? Yeah, so again, it should be a term that is symmetric under all the usual global symmetries of QCD. Yeah? So it should be SU3 left plus SU3 right plus U1 baryon number. So that's good. So one term is like this determinant U. Yes, and it should also be a term that is explicitly violating the axial symmetry. Yes, so that because that's what is if the axial symmetry was exact, then you couldn't possibly have a mass for the eta prime. Yeah, so that determinant U, that's perfect for that, yes, because all the pions, the light Goldstone bosons drop out from that term, yes, but it will keep the phase of the U matrix. So this one has an explicit dependence on the eta prime, yes, and then the remaining requirement is that it is invariant under this combined transformation, yes, where the theta and the eta prime are going to be shifted. Yes, so that's how I know that if I have a term determinant U in the chiral Lagrangian, I should write an e to the minus I theta in front of it. Yes, because here the determinant U has a phase that is e to the f times eta I f times eta prime. Yes, because it's an f by f matrix and it has an overall e to the I eta prime factor. So this combination here is the one that is invariant under the combined transformation of the theta and the eta prime. Yeah? So if there was a determinant U term, then it should come with an e to the minus I theta in front of it. Yes? Or if you write it out in terms of the eta prime, yes, then again you just expand it, and this is just a cosine potential. So in some sense this is satisfying. Yes, it would give you a mass term that is actually pretty large, of the order of lambda QCD. So you say maybe this is the right thing. Yes. Now the other thing that I want to emphasize is that if this was the right description, then you would plausibly identify this in an instanton effect. Yes, because instantons come usually with a prefactor e to the I theta. So the way you know that is that the instanton has a particular action which is e to the minus 8 pi squared over g squared, and you know how to combine the g and the theta into an overall factor. So every instanton effect usually comes with an e to the I theta in front. Okay, so if this was the right Lagrangian, then again this you could say that this is probably an instanton generated mass for the eta prime. Okay, and again, as I said, it is consistent with the Spurian analysis for the axial V1, which is that it's invariant under the simultaneous shift of the theta parameter and the eta prime. Okay, very good. So now, of course, the eta prime is very heavy, yes, because it has a mass of order lambda, so you can go and get an even lower energy Lagrangian, so below the scale of the eta prime, and then this is how you get the Lagrangian that is usually used for axion physics. Yes, so you integrate out the eta prime, and you now have just the theta prime, which is theta bar, yes, which is a linear combination of the complex phase in the quark masses, yes, and the theta parameter. So it's a simple exercise, to take this Lagrangian. Sorry, previous page. Just take this Lagrangian, yes, and integrate out the eta prime, and now you're going to get this Lagrangian here. And again, this is what is usually used for axion physics. That's because the expectation is, and now I'm talking about the hypothetical QCD axion, yes, because I'm asking now, okay, so if there was another symmetry, yes, then the dependence of the axion can be traced back by looking at the theta dependence of your chiral Lagrangian. Okay, so right now, if you want now just the pure axion physics, yes, you can go ahead and also integrate out the pions, yes, and then you just get the theta dependence of the minimum of the QCD potential. Yes, so this is what is written, in every textbook, and there's usually the first line of every paper about the QCD axion. Okay, so again, if you have a QCD axion, that would mean that there's a separate U1 axial symmetry, yes, one that is not identical to the axial symmetry of QCD, under which the axion would be the Goldstone boson, yes, and the theta parameter would also shift. Yes, so again, this Spurian analysis will then allow you to see what the axion dependence of your Lagrangian would be at low energies, and so this is the one. Okay, so now one thing that we did that is really simple, of course everybody knows what the mass of the axion is, but we haven't seen any simple derivation of the axion mass, of the analytic formula of the axion mass when there are more than two flavors. So people kind of know what that formula is, but it's just a little bit of an aside that it's actually really easy to get from here to the mass formula for the axion in the case when you have a lot of flavors, because rather than trying to diagonalize an F by F matrix here, yes, which is what people usually say. Well, of course, what you're supposed to do is you're supposed to just say, well, the pions are still much heavier than the axion, so just integrate it out, and then you will immediately get the expression for the axion. Okay, so again, it's something. Again, it's a minor thing, but since we haven't seen this derivation in any book, I just wanted to make sure that people understand that it's very easy to find it. Of course, for two flavors, of course, you can just go ahead and directly do the calculation. But when you have more flavors, you can still do it by integrating out all the pions. And of course, for f equals 2, you get the usual expression for the axial mass. Okay, so that's a little bit of an aside. Okay, so now let's come to Marcus's question. Yes. What else do we know about QCD? Yes, so one thing that we do know is that actually the anomaly. So the anomaly is non-zero, yes, but you can ask the question: what happens if you increase the number of colors in the large n limit? Yes. So what happens is that, of course, this is the expression for the anomaly as I mentioned on the first slide. But then you want to take the large n limit, and the way you take the large n limit is that you hold the 't Hooft coupling fixed. Yes? So the 't Hooft coupling is g squared times n. So you put in a factor of n here, and then that combination is held fixed. So this is what I call lambda, and then it goes like 1 over n. Yes? So actually the anomaly is a 1 over n effect. Okay, so which means that in the large n limit, the anomaly goes to 0. Yes, so in the large n limit, this eta prime, this particle that is heavy in QCD, but would be the Goldstone boson, actually will have to start becoming a true Goldstone boson again. Okay. However, the potential that I wrote for you here, yes, of course, no, I didn't fully explain it here, yes, because F also has some scaling with n, yes. But if you look carefully at the expression that I wrote for you as the so-called instanton contribution to the chiral Lagrangian, it actually doesn't vanish for large n. Okay. And I'm not the first to make this up. Whitney in 1977, one of his first papers on QCD said, naively we could write this determinant U term as a contribution to the chiral Lagrangian, but it obviously cannot be right because the eta prime mass doesn't go to 0 in the large n limit. Okay? And what he argued was that actually the eta prime mass should go like 1 over n, exactly like 1 over n. And there were several ways that he was able to see that. One was, he was just able to get an expression for, what the theta dependence of the pure QCD vacuum energy should be. He was also able to just do some large n power counting, and so the expectation is again that the eta prime mass should go like 1 over n. This which will tell you that.
Is there really an n squared out front?
Yes.
Doesn't that give you that it's independent of n? You expand to quadratic order of theta?
No. No. I think it's just a function of yeah. I think the n squared just comes from the fact that there is
the kinetic term, I think.
Is the number of gluons or something like that. So there is really an n squared. So what this tells you is that our form of the chiral Lagrangian that I wrote before, where I just had this e to the minus I theta times that u, that can be right. Yes, it has to be somewhat more complicated. And the simplest way to sort of implement Whitney's rule is to say, well, it's the nth root of this determinant n term. He never really wrote it in this form, but I think this is kind of what he meant would be one possible term, one possible. He essentially just wrote, this expression here, where the eta prime mass goes like 1 over n. But anyway, this is one term that would have the kind of properties that satisfies all the symmetries and the large n limit. Okay. But now you should start shouting. What does this mean? Yes. Now I have nth roots in the potential. Yes. And in particular, what is most bothering about this would be that the one thing we know about the theta term in QCD is that physics should be 2 pi periodic in theta. Yes? So if I now write out what kind of potential I get for the eta prime, it would actually be, rather than this cosine theta minus f times eta prime, it would be cosine f theta minus f eta prime over n. Yeah, so it wouldn't be 2 pi periodic. So physics would not be 2 pi periodic. So that on its own seems like a problem. Yes, but of course Whitney is a genius, so he immediately in the same paper immediately said no problem. Yes, no problem. It just means that the theory has to have several branches. Okay, so that the dynamics of QCD has to be such that there are actually several branches showing up. Yes, and the way the 2 pi periodicity is going to be restored is that, again, you will have these different branches. Each of them is going to have a potential of the sort that I wrote for you with the 1 over nth root, or something like that. But then k is telling you which branch you are on. Yes, and the way what happens is when you shift theta by 2 pi, yes, you are at the same time jumping from one branch to the other branch. Okay, so one way to see it is to say that, okay, so let's try to, you know, get, for example, what the theta dependence of the of QCD would be. Yes, with this branch structure. Yes, so there would be this, let's say n equals 3, so there would be these 3 branches, and the minimum, depending on what theta actually is, would be lying on a different branch, yes, and at some point you would be jumping from one branch to the other branch, yes, and if you just look at this lower envelope here, which is the true minimum of the QCD potential as a function of theta, now this is 2 pi periodic. Okay. And here, I guess this one is, now here this would be one of those potentials that also includes the eta prime and has the eta prime dependence. So anyway, so you get the idea that you know, large N limit forces on you having this branch structure, and this branch structure is going to restore the 2 pi dependence, the theta 2 pi shift invariance in this sort of non-trivial way. Okay. Yes?
I'm a little confused. Are those other branches like physically accessible excited states, or do they just like not exist now? We only forever stay in the lowest branch?
So that's a really good question, and you know, so these should have physical consequences, yes, but you know, the magnitude of these excitations, yes, you know, of these barriers is of the order of lambda QCD. So once we are at low temperatures, yes, we are just going to be sitting at one of these minima in one of these branches, and that's that. But I think, you know, sometime in the early universe, you know, these branches must have come alive. And I would really love if anybody has ideas of how to, you know, design a cosmological test for this branch structure of QCD. I think that would be something really interesting, because my guess is, you know, for example, you know, so one thing that we did check is, you know, does it make any difference for the axial potential? And it turns out the fact that you have these many branches doesn't make any difference for the low temperature dependence of the axial potential. Okay, because in fact, you know, you are just sitting at one of these branches, and you know, the presence of these others is not going to change the, you know, the expression for the axial potential. But once you have reached energies of the order of lambda QCD, you know, I mean, all of this is available for you. So my guess is there's got to be some important cosmology, but you know, I don't have an answer to that. So that's something that I would very much like to know.
Okay.
Doesn't it give you domain walls?
Yeah, possibly. But again, you know, do they survive, or I don't know. So again, this is something that we could think about. Again, I haven't thought that much, but this could be one of the most interesting questions. Yeah. You would think axions should have some of these dimensions. Yes.
Just to get a sense of the scale here, you said we need temperatures of order lambda QCD.
Yeah.
Is that a temperature that's like achievable in a like nuclear collider like RIC, or is that like Big Bang level temperatures?
I think the people in RIC claim that they, you know, I mean, don't they claim that they get quark gluon plasmas? So
Yeah, they keep discovering it every 5
yeah,
years.
so I think they claim that those are achievable, but I don't know how much you can actually say with billions of how many particles do they have in one collision.
It's not relevant to this.
I don't know. I mean, if you have seen any picture of a RIC collision, yes, then. Anyway, so I think, you know, these are, I think, really interesting questions, and again, you know, these are things that are really about ordinary QCD, yes. So, you know, okay, maybe you have an axial, and maybe you don't, but again, it's not really made up physics. So this is the way our world is really supposed to be working. So there you go. So yeah. So just another comment, yes, is, you know, so why is it that at the minimum we are not really very sensitive to, you know, all these branches, Yes, and the answer to that is just that actually the eta prime itself is like an axion. Yes, so the eta prime is like a QCD scale axion. Essentially, what it's trying to do is it is trying to cancel the theta dependence from your potential. Essentially, I mean, you can see that eta prime and theta are essentially linked together with the anomaly equation. Yes. So essentially, what happens is that at the minimum, the eta prime that is just going to adjust itself such that the theta dependence just completely cancels out of the QCD Lagrangian. Yes. Now, once you have an explicit breaking, yes, then the explicit breaking term will sort of restore the theta dependence. But without an explicit breaking, of course, the eta prime would just completely wash out the theta dependence of the low energy effective potential. Okay, so again, in some sense, you can think of the eta prime already as an axion-like particle, yes, except, of course, it's not super light. Yes, it's of the order of the QCD scale and gets rid of all the theta dependence from your QCD Lagrangian at scales of order lambda QCD. Now, if you have these very small explicit breaking terms, yes, those will restore the theta dependence. Okay, so that's the usual story. So again, we are not really claiming a lot of credit for anything. Maybe some small things. This is mostly going back to Whitman in the 70s. What we have done is we were trying to check this picture in a cousin of QCD. We call this AMSB QCD, and I will try to explain in a moment what this means. And there were some related works by Michael Dine and collaborators, not too surprisingly, as he's also always interested in theta dependence and CT, strong CT problem a few years ago. Okay, so why are we going to supersymmetric theories? Yes, well, QCD is, of course, very interesting, but it's hard, because of the strong coupling, strong interactions, it's very hard to get some exact results. However, supersymmetry often gives powerful constraints on the strong dynamics. And in particular, for the supersymmetric version of QCD, Seiberg was able to nail down the phase structure of the theory, what is this now, 30 years ago, using a few techniques that can be applied to these theories, irrespective of whether the theory is strongly coupled or not. Holomorphy was the main tool that supersymmetry bought for you, namely that some quantities in the supersymmetric theories actually have to be holomorphic, so they have to be analytic, so they should only depend on a particular complex variable and not its complex conjugate. The 't Hooft anomaly matching conditions, okay, so those are, again, non-perturbative, very simple arguments that are telling you that if you have some global symmetry, then the anomalies in the high and the low energy theories should match. Sometimes you can invoke instanton calculations, and sometimes you can connect theories with different matter content, either by giving a VF to some fields or by giving a mass and integrating out some of the fields in the theory. So he was able to find the phase structure of this theory. Yeah, so this is the one that we call supersymmetric QCD. So it's an n equals 1 four-dimensional supersymmetric gauge theory, SUN with F flavors. So this is the gauge group here, and here is the global symmetries. So these are the SUF cross SUF chiral symmetries, the analogous ones to what we have in QCD. This is baryon number. Because of supersymmetry, there is another peculiar kind of global symmetry called the R symmetry. And again, one of the beauties of the supersymmetric theories is that there is something called the moduli space, which is sort of the direction in space that is actually going to be massless. So Marcus actually came up with this nice theorem. It's called the Muthi-Taylor theorem, where you can show that the moduli space, these d-flat directions, are actually parameterized by the so-called holomorphic gauge invariance. And what do I mean by that is, so these are chiral superfields, yes, and then you can make gauge invariance out of them without taking a complex conjugate. Okay, so if you take the independent holomorphic gauge invariance, those will be your low energy degrees of freedom. Okay, so if the number of flavors is low, then you don't have baryons, then you only have mesons. Once the number of flavors is above n, you also have baryons and mesons. Okay, so here is what Seiberg found. Okay, so this is a lot for one slide, but you don't need to understand every aspect of it. What I want to tell you is the story that as you change the number of flavors in SUSY QCD, so n is fixed, so n is the number of colors, and you change the number of flavors, actually the dynamics and the phase of the low energy theory changes very significantly. So if you don't have any flavors, f equals 0, so that's what we call the pure super-Yang-Mills theory. The dynamics is well understood. It's going to be a confining gauge theory, and the dynamics of confinement is going to be gaugino condensation. Okay, and I will get to that in a moment more. And the number of flavors is less than the number of colors. You will get something called the Affleck-Dine-Seiberg superpotential. And these two I will explain in a little more detail. And as you increase the number of flavors, you get other very exotic kind of phases, something called the quantum modified constraint, S-confinement, different kinds of, here you have a CFT, a conformal field theory, and another even more exotic phase called the free magnetic phase. Okay, so let me just tell you, for example, what happens when you have 0 flavors. So you have no matter fields. So in this case, there is no continuous flavor symmetry present in the theory. There was a U1R symmetry that was anomalous. Okay, so that one is broken to a discrete subgroup. Okay, and the dynamics that is consistent with this with the presence of this spontaneously broken, with this anomalous discrete R symmetry is gaugino condensation. So there would be a gaugino condensate that is proportional to the scale. So it is somewhat like the quark condensates in ordinary QCDs, except here I don't have any quarks. I have the superpartners of the gauge bosons, which are the gauginos, and in the vacuum they are forming a condensate. And the important thing is that there are actually n different branches. So for SUN, this omega k is the kth root, the nth root of unity, yes, and you take the kth version of that. So it's e to the, k times 2 pi I over n. Yes, that's what this omega k is. Very good. And you have this superpotential present. Okay, so this theory should be a truly confining theory, meaning that there is an area law for the Wilson loop. Okay. Now let me I won't go through all of it, but I want to show you one more example here. That's when the number of flavors is just less than the number of colors, but not 0. So I start including quarks in a supersymmetric way, but not enough many to have the number of flavors bigger than the number of colors. Then I get something that is called the Affleck-Dine-Seiberg superpotential. So this was again, actually this is now 40 years ago. It was calculated by these 3 people. And this superpotential has this very weird form. Yes? So it has determinant m in the denominator. Yes? And then it has some fractional power also showing up. Fractional power depends on the difference of the number of colors and the number of flavors. Now the nice thing is when the number of color minus the number of flavor is equal to 1, then you can actually show that this term, at least one piece of this term, is actually generated by an instanton. Okay, so you can go ahead and do one of those very few cases where you have a reliable instanton calculation, where everything is truly calculable because there's an IR cutoff for your instanton, because the gauge group is actually Higgs here, so you don't run into the usual problems with instantons like in QCD where, the gauge couplings become stronger and stronger as you go to the IR, and, the instanton effects become more and more important, yes, but then at some point you lose control over them. That's not happening here. The instantons do become more and more important as you go towards the IR, but at some point it's being cut off by the fact that your gauge group is being hexed. Okay, so again, for one particular case, you can go ahead and do this exact calculation and show that this term is really generated. And then, once you have established it for one particular number of flavors, as I said, you can use these tricks by Seiberg where you can sort of integrate out a flavor and establish it for all the other flavors. Okay, very good. So in this case, the gauge group is broken. Yes, for f equals n minus 1, it's completely broken. If f is less than n minus 1, yes, then there is some subgroup that is unbroken, and that subgroup that is unbroken will have a gaugino condensate. And in that case, that's the dynamics for generating this Affleck-Seiberg superpotential. Once it's completely broken, then of course it's the instanton. Okay, very good. So this is, again, just to go back to the phases of supersymmetric QCD. Okay, so again, this is a beautiful picture. Many of us have played a lot with it. Cynthia, Marcus, John, and I, this was our childhood, yes. Now, the problem is that this is very different from what we expect in non-supersymmetric QCD. Non-supersymmetric QCD lattice simulations suggest that there are essentially only two different kinds of phases. Okay, so one is the one that you're used to. You have chiral symmetry breaking, and SUF cross SUF is broken to SUF diagonal. Yes, and once you have a large number of flavors, perhaps as high, I'm not sure how well they know this boundary from the lattice theories yet, but it's somewhere around f equals 3n. You do go into a conformal phase, and then you're not going to have confinement and chiral symmetry breaking anymore. Okay? So again, these two look very different. Yes, you see you have here 1, 2, 3, 4, 5, 6 different things, yes? And essentially none of them look like the phase in ordinary QCD. Maybe this one you can sort of make an argument is somewhat similar, but so you would like to start making some connections with and of course, again, this is not a new story. I mean, Cynthia did this. When was this? When you were 98, or you started doing that, and Marcus heard a lot about it too. So we were trying to go by this proposal of Hitoshi, where he suggested that we should just try to use a particular form of supersymmetry breaking, which is anomaly mediation, which is, as I will argue, is a very particularly suitable way to be able to get the exact results in the supersymmetry breaking, in these supersymmetric theories, once supersymmetry breaking is added to it. Okay. Now, initially, I would like to remind you, and of course, Marcus was one of the first to write down these theories of AMSB. Hitoshi, Ricardo, and John, yes?
And Rahman and Lisa. Yeah.
And then Lisa and Rahman, of course, separately, yes. So initially it was designed to provide a specific implementation of the theory of the weak scale and the particular embedding of the standard model into supersymmetry and give a predictive pattern for the soft supersymmetry breaking terms. Okay, so that's what it was originally designed to do. Now, here we are not going to try to do that. Yes, we don't care. Well, of course we care, but we are not trying to build a theory of the electroweak scale or of the Higgs hierarchy. We are simply trying to study the phases of some gauge theories. Okay? That's the only purpose here of doing AMSB. Yes, so we use the same acronym, but in terms of the goals, it's kind of different. Of course, the techniques are exactly the same. Yes? And just to say a few words about AMSB, again, in their construction, what they had is that the supersymmetry break. There was a supersymmetry breaking sector, yes, and then there was the visible sector, and there was no direct interaction between the SUSY breaking sector and the matter sector. It was purely mediated by supergravity. So there was a little bit of a cartoon like this. So there's the hidden sector and the visible sector. So they assume that the matter sector is sequestered. Again, here are the authors again. The important thing for us is, this whole story about supergravity, etc., is not going to really play an important role. As Ricardo and Alex Pomeroy pointed out, the effect of anomaly mediation on the visible sector can actually be all summarized in terms of a simple story related to conformal symmetry. Yes? So essentially, all the supersymmetry breaking can be incorporated into a single sort of Spurion superfield, yes, this so-called compensator, which is making up the dimensions such that the theory would actually become conformal, so scale invariant, yes, and the F term of this conformal compensator is going to be the source for supersymmetry breaking. Okay, and so the effect of supersymmetry breaking will simply show up, by these insertions of these conformal compensators in the superpotential. You have to put in a phi cube term because it's dimensions 3 for supersymmetry, and for the Kähler potential you have to put in a phi dagger phi. And that's all that is essentially needed for us from the whole AMSB picture. And the reason why this is so powerful is because, as you can see, this is a very nice way of being able to see how the supersymmetry breaking terms are actually mapped through the strong dynamics. Yes? So that's what is powerful about it. That there is sort of a simple Spurion analysis that you can do both in the electric and in the magnetic, or the original and the dual theory, or whatever you want to call it. Yes, and it will uniquely tell you how to map the supersymmetry breaking through the strong dynamics. Okay, so for example here, there's a little example. Yes, if the matter sector is conformal, then of course you can scale out the supersymmetry breaking by this transformation, and if you remove the supersymmetry breaking out of it. So SUSY breaking will be tied to violations of conformality, and this is UV insensitive. So really, you can do this within the effective theory. Yes? So it really doesn't matter what happened in the theory at high energies. Yes? So all you care about is, what the theory at a given scale is, and at that scale you will be able to see what all the effects of supersymmetry breaking are. Okay, so scale invariance could be broken via the RG running. So that tells you that whenever you have a non-vanishing beta function, you're going to get some supersymmetry breaking terms. So for example, we will get a gaugino mass that is proportional to the gauge beta function. Yes, so you get some scalar masses that are proportional to the anomalous dimensions, A terms, etc. So if you do this in the SUSY QCD case, the beautiful part that you will find is that, of course, you will get some gaugino mass, and the scalar spark masses will be always positive as long as the theory is asymptotically free. Yes? Of course, this was a problem when you try to do this for the MSSM, yes, because there, when you had the right-handed slaptons, yes, they were getting a negative mask there. But as long as you're talking about just, asymptotically free gauge theories, these quark masses will always be positive. Yeah, so that means that, in fact, at some scale, you are starting with sort of the perfect UV boundary conditions, in the sense that, let's say, for SUSY QCD, you're starting with a theory. If you added AMSB to it, there you have positive quark masses and you have some non-vanishing gaugino masses. So, in some sense, it is sort of somewhat like QCD. Of course, it's not exactly QCD, because I can't take these masses to be really large. I can't remove them from the spectrum, yes, because then I'm back to ordinary QCD. So I still want to treat them as small perturbations. Yes, but still, at least the massless spectrum is going to be that of ordinary QCD. Then I'm going to get these other particles that have a little bit of supersymmetry breaking, and then you hit the QCD scale. Okay, one sort of additional piece that probably you guys knew, but I wasn't aware of, and this is what made the difference for Hitoshi, is that of course, when you have a tree-level superpotential term present in the theory, then there will be an additional term in the Lagrangian that is directly related to the tree-level superpotential in the theory. Yes, clearly it's related such that if you had a phi cube, yes, then it would be exactly vanishing, yes, because that would be the scale invariant theory. But if it's not a phi cube, then that term is actually going to give you an additional non-zero scalar potential. Yes. So here, this is a term in the Lagrangian. So this is a piece in the scalar potential. Yes, that is evaluated from the tree-level superpotential term that may or may not be conformal. Yes, and then we also generalize this for generic Kähler potential. Doesn't matter. So what Hitoshi showed, for example, is that for these cases that when the number of flavors is less than the number of colors, I argued to you that you have something called the ADS superpotential. Yes, and usually the law about this is that this doesn't have a stable vacuum, yes, because this has these fields in the denominator, and so they want to become very, very large, so your vacuum is going to run away to infinity, and so that's what the ground said, it has a runaway vacuum. Actually, once you add the contribution from AMSB to the usual ADS superpotential, then you will actually get another term with the opposite sign that is going to stabilize the supersymmetry, that is going to stabilize the vacuum at a finite value, so there will be no runaway superpotential in this case. Okay, so it's a non-perturbative effect that involves supersymmetry breaking. Yes, so this is the form of this additional piece. And again, AMSB allows us to pin down this non-perturbative term with supersymmetry breaking in it. Okay, formally tree-level, but again, it is a non-perturbative effect. And it will stabilize the ADS superpotential, and it will give you the appropriate symmetry breaking pattern. So it will give you SUF cross SUF broken to SUF diagonal, just like in ordinary QCD. Okay, so the massless degrees of freedom in this case will be just like for QCD, the ordinary pions. Okay, so now once you have a theory like this, you can go ahead and start calculating chiral Lagrangians. Yes? Before we couldn't really do this because we didn't have even the right symmetry breaking pattern with a stable minimum, etc. Yes, but now we have a stable minimum, the right symmetry breaking pattern, so we can go ahead and calculate chiral Lagrangians for this.
So, I mean,
Yes.
this was a long time ago, but so first of all, physics point is that you don't need AMSB to do this because this is all at weak coupling.
Right.
If you have a small, I'm saying, I know you know this, but I'm saying this also so other people know this, because you didn't say it, that if the soft breaking masses are small, then everything that's happening here is happening at weak coupling,
Right.
and so you don't need anything other than tree-level physics, just minimizing potentials to solve all of this. And the second thing is that...
So AMSB is only useful really when you have those phases that are not weakly coupled, yes.
Right. So AMSB is in more non-trivial cases.
So in
it
fact,
gives you additional information.
Just to say,
But,
so Dyn et al. Were the ones who actually did this, just without AMSB, just adding the soft breaking terms and.
I think it was even before that. That's the other thing I was going to say,
Okay.
is that my memory is that there was a paper by, I think it was Peskin, and I think it was somebody from Israel, like Sonnenschein or
Right. So
something.
they did, but they
And
didn't
they
didn't even find stable minima.
Yes, they did. They absolutely found cases where you had the correct QCD structure. That was the main point of that paper. So, I mean, that was done in, I don't know, the late 80s or early 90s or whenever it was. It was right around the early time of this. And it worked, you know, anyway.
They certainly didn't do the eta prime potential.
Right.
No, I agree they didn't do everything, but I don't know why we're, you know, referencing Moriyama in 21. I don't know, did he reference these papers? Did he know these papers existed? This was done a long time, a lot of this stuff was done a long time ago. It's not saying nothing is new, but I don't know.
Certainly, all of my papers referenced, you know, Shimon and Kobe.
Yeah, well, this was, okay. Maybe you can reference it in your talk also.
Very good. So the thing that I would like to emphasize also is that once you go through all of these different phases that you see in supersymmetric QCD, yes, and add the supersymmetry breaking, yes, actually what you find is that the picture will collapse to something much more similar than we had in ordinary QCD. Okay, so here again, QCD-like here, and F equals n. There is a branch that is non-calculable, so we don't really know where the minimum of the theory is. Yes. However, there is at least a local QCD-like vacuum. Okay, here is a QCD-like. If you go into the conformal theory, yes, there is at least a local QCD-like vacuum, but there may be a runaway direction as well. Okay, and then up here again you can argue again that it's QCD-like. So the theory looks very much like ordinary QCD, yes? And of course, F greater than 3n, is where in ordinary QCD you should see the conformal phase showing up. Yes, but of course, you know, we can't reach that with the supersymmetric theories. Certainly not with the AMSB, yes, because that's where the supersymmetric theories stop being asymptotically free. Okay, very good. So now we went ahead and calculated the eta prime potential for the cases with the MSB. Yes. So first, you know, we looked for the case when the number of flavors is less than the number of colors, and you add the quark mass, yes, because we are trying to also take into account the effect of the explicit breaking term, yes. So you can go ahead and calculate the meson web as usual, you know, up to some small perturbations in the quark masses, and then you can go and get, you know, essentially the entire chiral Lagrangian, but we were only interested in the eta prime part of it, yes. So you can set it to be the phase of the quark or the meson superfield. Yes? So you can go ahead and find, you know, exactly what your chiral Lagrangian is, and from there you can, you know, just carry through and get the eta prime dependence of your chiral Lagrangian. And so the structure that we are finding is very much like what Whitten predicted. Yes, if you remember again from the very beginning of this talk, I told you that it should be eta prime over n. Yes? So we are finding that kind of branch structure here, yes? But instead of eta prime over n, we are finding eta prime over n minus f. Yes? And then again, the k is telling you, you know, which branch of the theory you are actually setting up. Yes? And of course, for pure QCD, when f equals 0, you get exactly Whitten's prediction, and again, you know, Michael Dine had this also in his case, where he did it the way Marcus said it, without the MSB, just adding some soft breaking terms. And again, you know, for small number of flavors, yes, you're also going to get the kind of predictions that you expected. Okay, 1 over n. Okay, now, when the number of flavors is equal to the number of colors, the situation is going to be very different. So we can look at several different cases. Yes, we can fix f equals n minus 1, or later on we can go to f equals n, or n plus 1, etc. Yes, so in this case, when f equals n minus 1, we are actually not going to find any branches in the theory. Yes? And the potential in theta is actually directly proportional to a cos theta. Yes? So you would say, well, I told you there are no instanton effects. But for f equals n minus 1 is the one case in supersymmetry where you know that there are instanton effects. Yes? So maybe you shouldn't be shocked that in that case, actually, you know, the eta prime potential is a direct instanton effect. Yes? There are no branches, and the eta prime mass doesn't go to 0. Yes? So the large F, large N limit is qualitatively different from the large N fixed F limit. Yes? And when n minus f is greater than 1, again, we have this potential that is eta prime over n minus f. We know it's not an instanton effect, and we are also not shocked about it in supersymmetry because we know that it's coming from gaugino condensation. Yes? So we can identify the dynamics in supersymmetry that is responsible for the generation of the eta prime mass, and that is gaugino condensation. Okay. For f equals n minus 1, it is an instanton effect, and again, there are no branches in this case. Yes? So in this case, the eta prime mass does not vanish for large n, yes? But that's again also not super shocking, yes? Because of course the anomaly goes with f over n. Yes? So I told you if I hold f fixed and go n to infinity, take n to infinity, the anomaly goes to 0, yes? But if I take f over n fixed, then of course, you know, the eta prime mass doesn't necessarily have to go to 0. Okay. Now, which one is QCD? Of course, you know, we don't really know which one is the correct large n limit.
Did you identify the mechanism when f is less than n?
It's gaugino condensation.
I thought that was
When f is less than n, it's gaugino condensation. It's whatever generates the Affleck-Dine-Seiberg superpotential, which is the gaugino condensate. And also, you're not shocked why it's f minus n, yes, because that's the unbroken gauge group, yes, because you have f squarks, they all get a VAV, so you have an SUN minus f unbroken gauge group, and that produces gaugino condensation. When f equals n minus 1, it's an instanton. When f equals n or n plus 1, so that required additional care, yes, because in that case we don't have the Affleck-Dine-Seiberg superpotential, so here we really had to use AMSB, so we did this. And what we find is no branches. It is consistent with being an instanton effect. But of course, the theories are strongly coupled, so we don't really know. We can't do a reliable instanton calculation here to verify it, but it looks like, you know, they are instanton effects, both for f equals n and n plus 1, so I'm not going to go through this. And when f is greater than n plus 1, yes, then we have a Seiberg duality, and we can go through with the analysis in the Seiberg dual. And actually what will happen is that in this case there will be a gaugino condensation in the Seiberg dual SU f minus n theory. Okay? And now there will be f minus n branches. So that's the whole story essentially, and so essentially it's going to be symmetric in the n minus f and the f minus n. All right, very good. So softly broken SUSY is a nice lab for studying confinement. AMSB is a nice way to implement that because again it's UV insensitive and it's easy to match to the duality due to the dependence on the scaling properties. We were able to calculate the eta prime potential and the theta dependence, and these are giving you some hints for the dynamics of the confinement. For ordinary QCD, the guess is that it's not instantons and there's some branch structure. For the n equals 1 case, the one that we calculated, you get this branch structure where the number of branches is equal to n minus f. When n minus f is equal to 0 or 1, then it is consistent with it being an instanton effect. All right. Thanks very much.
Questions?
potential, what phenomenon is at a scale that the bed of eta prime is with, like the proton structure, neutron structure, or it has to be like the big bang?
Sorry, what phenomenon is around the mass scale of the eta prime?
Like the bed, you mentioned there can be a eta prime bed,
Yes.
but
Yes.
like in order for that to have a bed,
The eta prime does have a valve.
like
It has a valve.
yes,
There, it's, it's not a question, yes.
like it is. So like is the eta prime we observed in Kreider the
Yes,
structure?
it's a fluctuation around its valve,
Ah.
right? So that usually is subtracted out.
So the eta prime bed and axion bed are like similar in terms of the strong CPU problem? Or?
No, so again, the eta prime is, as I mentioned, you can think of it as the axion, the QCD scale axion, and it gets rid of the theta dependence of the theory at the QCD mass scale. Yes? But because it's a heavy object, it cannot get rid of the dependence at low masses. Yes?
So the neutron is still at low
I'm
masses.
sorry, the neutron, no, the neutron is QCD scale. Yes? So, but the quark masses, yes, M up and M down, those are much lighter than the QCD scale. Yes? So the axion potential is usually related to the up and the down quark masses. Yes? I mean, they are proportional to M up, M down, etc. Yes? So that the eta prime cannot get rid of
So
because
guess,
it's so much heavier. Yes.
I guess I'm just confused now.
So okay, so you have the theory at the QCD scale, yes,
Yeah.
and the eta prime mass is at the QCD scale, and you have these very small explicit breaking terms, which are the quark masses. Yes, if there were no quark masses, the eta prime would completely get rid of all the theta dependence in QCD. Which, of course, that would mean that you have massless fermions, and there are many different ways of explaining why there wouldn't be any theta dependence. But one way to explain it is that the eta prime cancels it. Yes. Now you do have the explicit breaking terms, yes, but they are very small. Yes, so the eta prime cannot cancel them. Okay.
No more questions? Let's thank the speaker again.